La luz viaja at 300,000 kilometers per second, crossing the vacuum of space as a silent messenger of the universe. It is the fastest speed in existence, the absolute limit of reality as we know it. Yet it also represents our most fundamental cosmic prison. Imagine for a moment that you could travel at that speed. In a single second, you would circle the Earth 7.5 times. You could reach the Moon in little more than 1 second. You would reach Mars in a matter of minutes. It would seem like the perfect ticket to explore the stars, to become a truly interstellar civilization. But there is a problem so profound that it challenges the fundamental laws of the universe. We will never achieve it. It is not a matter of insufficient technology. It is not that we have yet to build the right ship or discover the correct fuel. It is something far more absolute. The laws of physics, written into the very fabric of space and time, categorically forbid anything with mass from reaching the speed of light. And the reasons are as strange as they are fascinating. When you attempt to accelerate toward that limit, the mass of your ship begins to increase, not by a little, but exponentially. As you approach the speed of light, your mass approaches infinity, and accelerating infinite mass would require infinite energy. All the energy of the observable universe would not be enough to provide that final push. But mass is not the only problem. Time itself begins to behave strangely. As you travel faster and faster, time for you slows down compared to the rest of the universe. Only months might pass on your ship, while entire centuries elapse outside. And if you somehow manage to reach exactly the speed of light, time for you would stop completely. You would literally stop experiencing the passage of time, frozen in an eternal instant, while the universe ages around you. And there are even more mysteries buried in this cosmic frontier. The very length of space contracts in the direction of your movement. Distances compress until they collapse. Causality, the relationship between cause and effect that sustains all logic, begins to crumble. The universe simply does not allow anything with mass to cross that threshold. So, we are trapped, confined not by a lack of ingenuity or ambition, but by the most fundamental laws of reality. The stars we see shining in the night sky, those points of light that seem so close, are actually separated from us by abysses of time that no spacecraft will ever cross in a human lifetime. Yet, understanding why we will never reach the speed of light is to understand something profound about the nature of the universe itself. It is to discover that the cosmos has rules, absolute limits that no future technology can violate. It is to confront our smallness before the vastness of space, but also to marvel at the mathematical elegance that governs all existence. If this exploration of the limits of the universe fascinates you as much as it does us, you are in the right place. At Scientia Nocturna, Night Science, we investigate the deepest mysteries of the cosmos, from subatomic particles to the observable confines of space-time. Join us on this journey to discover not only what we know about the universe, but also what we can never know. Tonight, we are going to unravel one of the most counter-intuitive secrets of physics. We are going to explore why the speed of light is not simply a record to be broken, but an absolute barrier woven into the very structure of reality. Prepare for a journey that will challenge everything you thought you knew about speed, time, and space. 300,000 kilometers per second. That is the number that defines our universe in ways we are only beginning to comprehend. It is not merely an impressive velocity. It is the speed at which information itself travels throughout the cosmos. It is the cosmic speed limit, engraved in the fundamental laws of physics, with the firmness of an immutable mathematical constant. To truly appreciate what this number means, we need context. In a single second, light covers a distance equivalent to circling the Earth 7.5 times along the equator. Imagine that. While you read this sentence, a ray of light could have circumnavigated our planet repeatedly. In that same second, light travels from the Earth to the Moon, covering the nearly 400,000 kilometers, separating the two celestial bodies with time to spare. Scale up a bit. Light from the Sun takes approximately 8 minutes and 20 seconds to reach the Earth. This means that when you look at the Sun, you are actually seeing what it looked like more than 8 minutes ago. The light that touches your face began its journey from the solar surface before you finished your breakfast, and that is our closest cosmic neighbor, a star that in astronomical terms is practically glued to us. Now multiply those distances. Proxima Centauri, the nearest star to our solar system after the Sun, is little more than 4 light-years away. 4 years of continuous travel at 300,000 kilometers per second. Andromeda, our closest neighboring galaxy, is 2.5 million light-years away. The light we see today from Andromeda began its journey when our ancestors were barely beginning to walk upright on the African plains. And here is the truth that defines us. 300,000 kilometers per second is not just fast, it is the absolute maximum. Nothing in the universe can move faster. There is no ship, no particle, no signal of any kind that can exceed that limit. It is as if the universe itself has established a fundamental rule: this far and not 1 kilometer more. But what makes this number so special? Why exactly 300,000 kilometers per second and not any other speed? The answer has to do with the fundamental structure of space-time, that invisible fabric that connects every point in the universe with every moment in time. The speed of light is not arbitrary. It is an emergent property of how space and time are intertwined, a direct consequence of the equations that describe reality at its most fundamental level. Think of it this way. Space-time has a geometry, a mathematical structure that determines how objects move through it. The speed of light is essentially the velocity at which perturbations in that fabric propagate. It is the velocity of causality itself, the maximum speed at which a cause can produce an effect. If something could travel faster than light, it could potentially arrive at its destination before it departed, creating temporal paradoxes that would cause all logic to collapse. And it is not just visible light that travels at this speed. All electromagnetic waves, from low-frequency radio waves to high-energy gamma rays, travel at exactly the same speed in a vacuum. Photons, the massless particles that compose light, have no other option. They are born, moving at 300,000 kilometers per second, and remain at that exact speed for their entire existence, regardless of whether they travel for 1 millimeter or for billions of light-years. Curiously, the speed of light also appears in totally unexpected places in physics. It is integrated into the equations describing electromagnetism, discovered by James Clerk Maxwell in the 19th century, long before Einstein revolutionized our understanding of space and time. Maxwell calculated the speed at which electromagnetic waves should propagate, based only on the electrical and magnetic properties of the vacuum. The result was surprisingly close to the measured speed of light, a crucial clue that light itself was an electromagnetic wave. But here is the truly fascinating twist. The speed of light is not really about light at all. It is about the structure of the universe. It is the maximum velocity at which any information or influence can travel from one point to another. It is the cosmic speed limit that governs not only light, but gravity, the interactions between subatomic particles, and every imaginable physical process. This limit creates our cosmic prison. Look up at the night sky, and you will see thousands of stars. Each one is so far away that its light has traveled for years, decades, centuries, or even millennia to reach your eyes. You are literally seeing the past because light takes time to cover those astronomical distances, and those are only the stars in our own galaxy, the Milky Way. Extend your vision further. There are approximately 200 billion galaxies in the observable universe, each containing hundreds of billions of stars. Most are so distant that their light has been traveling toward us since before the Earth existed. And due to the cosmic speed limit, the vast majority of those galaxies will remain eternally beyond our physical reach, no matter how advanced our technology becomes. Because here is the fundamental truth we will explore on this journey. It is not that we haven't yet discovered how to travel at the speed of light. It is that the laws of physics absolutely prohibit it. And the reasons are so profound and strange that they defy our everyday intuition about how the world works. The speed of light is the absolute limit of the universe, not a goal to be reached, but an insurmountable frontier. And understanding why that frontier exists is to comprehend something fundamental about the very nature of reality. 1905. Bern, Switzerland. A young patent office clerk of only 26 years is about to change our understanding of the universe forever. His name is Albert Einstein, and in that extraordinary year, he would publish 4 scientific papers that would revolutionize physics. One of them, titled On the Electrodynamics of Moving Bodies, contained an idea so radical that even the brightest physicists of the time would take years to fully accept it. The idea was simple in its formulation, but devastating in its implications. The speed of light is constant for all observers, no matter how they move. It sounds innocent, almost trivial, but hidden in that seemingly modest statement was the deepest secret of the universe. Space and time are not absolute. They are relative, malleable, intertwined in a unified fabric that Einstein would call space-time. To understand why this is so revolutionary, we need to step back a bit. Before Einstein, physics operated under assumptions that seemed like common sense. If you traveled on a train moving at 100 kilometers per hour and walked forward at 5 kilometers per hour, your speed relative to the ground would be 105 kilometers per hour. Speed simply added up easy, intuitive, obvious. But when physicists tried to apply this logic to light, they found something disconcerting. Experiments conducted in the late 19th century, particularly the famous Michelson-Morley experiment, revealed something impossible. Light always traveled at the same speed, regardless of how the observer was moving. If you approached a light source at high speed, the light did not seem to move faster. If you moved away, it did not seem to move slower. You always measured exactly 300,000 kilometers per second. This made no sense under classical physics. It was as if you ran toward a moving train and discovered that it approached you at exactly the same speed as if you were standing still. It contradicted all intuition. Physicists desperately sought explanations. Perhaps there was an invisible medium, a luminiferous ether that filled space and through which light propagated. But every experiment designed to detect this ether failed. The ether was absent. Einstein approached the problem from a completely different angle. Instead of trying to explain why the speed of light seemed constant, he simply accepted that it was. He made this a fundamental postulate. The speed of light in a vacuum is the same for all observers, regardless of their motion. And then he followed that idea to its logical conclusions, no matter how strange they seemed. The consequences were revolutionary. If the speed of light is constant for everyone, then something else must change, and that something is time itself. Einstein realized that two observers, moving at different speeds, would not only see space differently, but would experience the passage of time differently. Time is not a universal river that flows at the same rate for everyone. It is relative, dependent on the observer's motion. Imagine two identical twins. One remains on Earth, while the other departs in a spaceship traveling at 90% of the speed of light. For the twin on the ship, time passes normally. He eats, sleeps, ages, day by day. But for the twin on Earth, the traveler's time has dramatically slowed down. What is 1 year for the traveler is more than 2 years for the terrestrial twin. If the traveler returns after what was 10 years for him, he will find that more than 22 years have passed on Earth. His twin brother is now 12 years older than him. This is not science fiction. It is a direct mathematical consequence of special relativity, confirmed by countless experiments. Subatomic particles, called muons, created when cosmic rays strike the upper atmosphere, have a half-life of only 2 microseconds. At their speed, they should disintegrate long before reaching the Earth's surface, yet we detect them in large quantities at sea level. Why? Because from our perspective, their time has slowed down. They live long enough to complete the journey because they experience less time than us. GPS satellites orbit the Earth at speeds of thousands of kilometers per hour. Their internal clocks run slightly slower than clocks on the Earth's surface due to relativistic time dilation. If engineers did not compensate for this effect, the GPS system would accumulate errors of several kilometers per day. Your mobile phone works correctly because it incorporates Einstein's equations into its position calculations. Relativity is not abstract theory. It is everyday technology. But time dilation is only the beginning. Einstein also demonstrated that lengths contract in the direction of motion. If you travel at speeds close to the light, the space in front of you compresses. Distances literally shorten. From your perspective, in an ultra-fast ship, the trip to Proxima Centauri would not take 4 years. At 99% of the speed of light, the distance would contract so much that the trip could be completed in months from your frame of reference. Of course, for observers on Earth, more than 4 years would still have passed. Time and space are malleable, dependent on the observer. And this is where we get to the heart of the problem. As you approach the speed of light, these effects become increasingly extreme. At 90% of the speed of light, time slows down to approximately half. At 99%, time flows about 7 times slower. At 99.9%, about 22 times slower. The progression is not linear, it is exponential. And what happens exactly at the speed of light? Something impossible. Time stops completely. It does not flow slower, it stops. From the perspective of a photon, if a photon could have a perspective, the entire universe exists in one frozen instant. There is no before or after. A photon emitted at the Big Bang and absorbed in your retina now experiences no passage of time between those events. For the photon, both moments are simultaneous. This reveals a profound truth. The speed of light is not just a speed limit. It is the boundary where time itself ceases to have meaning. It is the frontier between what can experience change and what exists in an eternal present. And Einstein's mathematics show unequivocally that nothing with mass can cross that frontier, because here is the other secret Einstein discovered. Mass and energy are 2 sides of the same coin, related by physics' most famous equation, $E equals mc circumflex $2. Energy is equal to mass multiplied by the speed of light squared. This equation tells us that mass is concentrated energy, and energy can be converted into mass. It also tells us something crucial about why we cannot reach the speed of light. As you accelerate an object, you add kinetic energy, but according to relativity, that energy does not just increase your velocity, it also increases your relativistic mass. The faster you go, the more massive you become, and the more massive you are, the more energy is required to accelerate you even further. It is a vicious cycle that intensifies exponentially as you approach the speed of light. At 99.9% of the speed of light, your relativistic mass is more than 20 times your rest mass. Accelerating that last 0.1% requires more energy than accelerating from 0 to 99%. And as you get closer and closer, the energy required grows without limit. Mathematically, reaching exactly the speed of light would require infinite energy. Not a lot of energy infinite. Einstein did not give us a recipe for traveling fast. He showed us why there is a fundamental limit that no technology will ever overcome. The speed of light is not an engineering challenge. It is a basic property of space-time itself, as fundamental as the existence of the three spatial dimensions. And it all stems from that simple, revolutionary postulate: light travels at the same speed for all observers. In 1905, an unknown employee of a patent office in Switzerland discovered that the universe had rules stranger than anyone had imagined. And in doing so, he showed us why the stars will forever remain beyond our reach. There is a fundamental problem with accelerating anything that has mass up to the speed of light. And it is not the kind of problem that is solved with better technology or more efficient fuels. It is a problem that is engraved in the mathematical equations that describe reality itself. As you approach the speed of light, your mass increases, not by a little, but exponentially, and at the exact limit, your mass becomes infinite. Let me explain how this works, because it is one of the most counter-intuitive aspects of special relativity. When you are at rest or moving slowly, you have what physicists call rest mass. It is your normal mass, the one you would measure on a scale. But when you start moving at significant speeds, something called relativistic mass appears. It is not that your body is gaining extra atoms. It is that the kinetic energy of your motion contributes to your total mass, according to Einstein's famous equation. At everyday speeds, this effect is completely negligible. If you drive a car at 120 kilometers per hour, your mass increases by such a microscopic amount that not even the most sensitive instrument could detect it. Even in a supersonic plane or traveling at thousands of kilometers per hour, the increase in mass is insignificant. That is why Newtonian physics worked so well for centuries. At the velocities we experience in daily life, the relativistic effects are invisibly small. But scale those velocities. Imagine you have built an incredibly advanced spacecraft capable of reaching 50% of the speed of light, about 150,000 kilometers per second. At that speed, your relativistic mass would be approximately 15% greater than your rest mass, noticeable, but not catastrophic. Now, accelerate to 80% of the speed of light. Your mass has multiplied by 1.67, almost double. At 90% of the speed of light, your mass is 2.30 times greater. At 95%, 3.20 times. And at 99%, 7.09 times. Do you see the pattern? The increase is not linear. It is exponential, accelerating dramatically as you approach the limit. And here is the real problem. That growth never stops, never levels off. It continues toward infinity. At 99.9% of the speed of light, your mass is 22.37 times your rest mass. At 99.99%, 70.71 times. At 99.999%, 224 times. And so it continues, each additional 9 multiplying your mass by increasingly larger numbers without an upper limit. At the exact mathematical limit of the speed of light, mass becomes infinite. Now think about what this practically means. To accelerate something, you need to apply force, and the amount of force required depends on the object's mass. That is why it is harder to push a car than a bicycle. More mass requires more force for the same change in velocity. When your mass begins to increase exponentially, the force needed to keep accelerating you also grows exponentially. Let's do a thought experiment with concrete numbers. Suppose you want to accelerate a small spacecraft of 1 ton, 1,000 kilograms of rest mass, perhaps the size of a compact car reasonable. To take it from 90 to 91% of the speed of light, you would need to add a certain amount of energy. Let's call it $X. Now, to accelerate from 91 to 92%, you would need more than $X, maybe 1.2 times $X. From 92 to 93, 1.5 times $X, and so on. Each increment requiring proportionally more energy than the last. By the time you try to accelerate from 98 to 99%, you are expending energies equivalent to massive thermonuclear explosions just to gain 1 percentage point of speed. From 99 to 99.9%, you might need energy equivalent to the sun's total energy production for days or weeks, and you would still be 1/10 of a percentage point away from the limit. The calculations become truly insane in the last increments. To accelerate your 1-ton ship from 99.999 to 99.99999% of the speed of light, barely gaining an infinitesimal fraction of speed, you would need energy comparable to all that our galaxy produces in 1 year, and you would still not reach the limit. Mathematically, reaching exactly 100% of the speed of light requires infinite energy. Not a lot of energy, infinite. It is an asymptotic limit, a barrier you can infinitely approach, but never touch. It is like trying to count to infinity. No matter how high you count, there is always a larger number. No matter how much energy you apply, you always need more for that final infinitesimal increment. And there is no trick, no shortcut. Some might think, well, what if we build a really big particle accelerator? Current particle accelerators, such as the Large Hadron Collider in Switzerland, accelerate protons to more than 99.999% of the speed of light, but they never reach 100%. They cannot, and those are individual protons, subatomic particles, billions of times smaller than a single grain of sand. The Large Hadron Collider consumes approximately 200 megawatts of electricity when operating at full capacity. That is enough energy to power a small city. And with all that power, it accelerates protons, not spacecraft, not humans, but individual particles weighing less than 2 trillionths of a gram. Accelerating anything with human mass to those speeds would require literally astronomical energies. Consider this: the kinetic energy of a 1 kilogram object moving at 99.9% of the speed of light is approximately 6.5 times 10 to the power of 17 joules. To put that into perspective, it is equivalent to the energy released by 155 megatons of TNT, more than 3,000 times the power of the atomic bomb dropped on Hiroshima. That is for a single kilogram. A manned ship would weigh thousands or millions of kilograms. And remember, you would still be 0.1% away from the speed of light. Accelerating that last little bit would require even more energy than everything before it. It is a progression that never ends, a race that becomes exponentially more difficult with each step, approaching a goal that is mathematically unattainable. So, it is not that our current technology is insufficient. It is not that we need to discover new energy sources or build more efficient engines. The problem is fundamental. The laws of physics state that any object with mass requires infinite energy to reach the speed of light, and the universe does not contain infinite energy, not even remotely close. Some theorists have proposed creative ideas. What if we do not accelerate the ship directly, but instead warp the space-time around it? That is the concept behind the hypothetical Alcubierre warp drive. Or what if we find a shortcut through space-time, like a wormhole? We will explore these ideas later, but even these exotic concepts face massive problems related to mass and energy. The reality is simple and brutal. Infinite mass is an absolute barrier. There is no way to bypass it by conventional acceleration. Einstein showed us that mass and energy are inextricably linked, and that accelerating mass to the speed of light is mathematically and physically impossible. Not difficult, impossible. And this is not just a practical inconvenience. It is a window into how the universe works at its most fundamental level. The fact that mass increases with velocity tells us something profound about the nature of space-time, about how energy and matter are interwoven into the fabric of the cosmos. It is a limit that defines not only what we can do, but what can exist. Infinite mass is the first guardian of the cosmic speed limit, and it is only the beginning of why we will never reach the speed of light. Time is not what we think it is. For millennia, humanity assumed that time was a universal constant, a river that flowed at the same rate for everyone, everywhere, without exception. 1 second on Earth was 1 second on Mars, on Alpha Centauri, at the farthest edge of the universe. But Einstein showed us that we were profoundly wrong. Time is flexible, malleable, dependent on motion. And as you approach the speed of light, time does something truly extraordinary. It slows down to a complete stop. This phenomenon is called time dilation, and it is one of the strangest and most counterintuitive effects of special relativity. It is not an optical illusion. It is not a measurement error. It is a real and measurable consequence of how the universe works. When you travel at relativistic speeds, your experience of time fundamentally changes compared to that of someone who remains at rest. Imagine our two twins again. One stays on Earth, while the other departs in an ultra-advanced spacecraft. The ship accelerates to 80% of the speed of light and travels toward a distant star. For the astronaut twin, everything seems normal. He eats 3 meals a day, sleeps 8 hours every night, reads, exercises, and ages day by day. His clock ticks off the seconds at the same familiar rate. From his perspective, time flows exactly as it always has. But for the twin who remains on Earth, the story is completely different. When he observes the ship through powerful telescopes, he sees his brother moving in slow motion. Every action takes longer. His heartbeats are slower. The seconds on the astronaut's clock advance lazily. For every hour that passes on the ship, 1 hour and 40 minutes elapse on Earth. Time has literally slowed down for the traveler. If the astronaut travels for 10 years, according to his own clock, and then returns home, he will find that 16 years and 8 months have passed on Earth. He has traveled to the future. His twin brother is now almost 7 years older than him. The friends he left behind have aged significantly more. The world has changed in ways he did not experience. It is a one-way time machine, permitted and predicted by the laws of physics. And this is not speculative theory. We have measured it. Experiments conducted in 1971 by Joseph Hafele and Richard Keating took ultra-precise atomic clocks and placed them on commercial airplanes that flew around the world. When the clocks returned and were compared to identical clocks that remained on the ground, the clocks that had flown showed less elapsed time. The difference was minuscule, barely a few hundred nanoseconds, but it precisely matched the predictions of relativity. GPS satellites constantly experience time dilation. They orbit the Earth at speeds of approximately 14,000 kilometers per hour, much slower than the speed of light, but fast enough for the relativistic effects to be measurable. The clocks on those satellites run approximately 7 microseconds slower per day than clocks on the Earth's surface due to their velocity. If we did not correct this effect, the GPS system would accumulate position errors of several kilometers every day. Subatomic particles, called muons, provide even more dramatic evidence. These particles are created when high-energy cosmic rays collide with molecules in the upper atmosphere at altitudes of 15 to 20 kilometers above the surface. Muons are unstable and decay quickly, with a half-life of only 2.2 microseconds. Even traveling close to the speed of light, they should only travel about 660 meters before disintegrating. But we detect muons in abundance at sea level. How is this possible? Because from our perspective, their time has slowed down dramatically. They travel so fast, typically at 98% of the speed of light or more, that they experience much less time than us. What is tens of microseconds for us is only a few for them. They live long enough to complete the journey because time itself passes more slowly in their moving frame of reference. Now scale these effects. At 80% of the speed of light, time slows down by a factor of 1.67. At 90%, by a factor of 2.30. At 95%, 3.20 times. The progression accelerates dramatically. At 99% of the speed of light, time flows 7 times slower. 1 year for you would be equivalent to 7 years for the rest of the universe. At 99.9%, the time dilation reaches a factor of 22.4. A journey that lasts 1 year for you would mean that more than 22 years have passed on Earth. Your children would have grown up and aged. The political, cultural, and technological world would be unrecognizable. You would have jumped more than 2 decades into the future in what was a 1-year trip for you. At 99.99%, the factor is 70.7. At 99.999%, 222.4. The numbers grow exponentially without limit, and at the exact mathematical limit of the speed of light, the time dilation factor becomes infinite. Time stops completely. Think about the implications. If you could somehow travel exactly at the speed of light, you would experience no passage of time. 0. For you, the journey from one end of the universe to the other would be instantaneous. But for the rest of the universe, billions of years would have passed. It is a paradox so extreme that the very concept of experiencing a journey at light speed ceases to make sense. Photons, the particles of light that travel at this exact speed, do not experience time. From the perspective of a photon, if it could have one, its emission and absorption are simultaneous events. A photon emitted by a star 13 billion light-years away, traveling for almost the entire age of the universe before entering your eye, does not experience that journey. For the photon, both events, its creation in an ancient star and its absorption in your retina, occur in the same instant. This reveals something profound about the nature of time itself. Time is not a separate entity from space. They are aspects of a unified structure, space-time. Movement through space affects your movement through time. There is a kind of conservation at play. You move through space-time at a total velocity that always adds up to the same amount. If you increase your velocity through space, your velocity through time must decrease proportionally. Objects at rest travel through time at maximum velocity. They move toward the future at 1 second per second, if you can say so. But when you start moving through space, part of your velocity through space-time is redirected from time to space. The faster you move spatially, the slower you move temporally. And at the speed of light, all of your velocity is directed through space. There is nothing left for movement through time. This exchange between space and time creates extraordinary consequences. Imagine you could travel at 99.999% of the speed of light. You could cross the entire galaxy, 100,000 light-years in diameter, in what for you would be only a few hundred years. Not because you are traveling faster than light, which is impossible, but because time for you has slowed down so much and distances have contracted so much that the trip becomes feasible within a lifetime. But here is the devastating problem. When you return home, you will find that more than 100,000 years have passed on Earth. Everyone you knew is dead millennia ago. Human civilization has evolved beyond recognition, or perhaps has become extinct. You have traveled into the future irreversibly. There is no way to return to your time. Time is a one-way arrow, and you have followed it much further ahead than the rest of humanity. This is one of the fundamental reasons why reaching the speed of light is impossible for anything with mass. At that exact limit, time stops completely. Causality breaks down. The very notion of before and after ceases to have meaning. It is a mathematical singularity, a point where the equations explode toward infinity and physics, as we know it, collapses. The universe does not allow anything with mass to reach that state, because doing so would violate the most fundamental principles of how reality works. Time must flow, causes must precede effects, and at the speed of light, these basic rules crumble. So, time itself is a guardian of the cosmic speed limit. It does not just slow down as you accelerate. It stops completely at the limit, creating a fundamental barrier that separates what can exist from what cannot. And that barrier is absolute. Let's run the numbers real, concrete numbers that reveal the absolute magnitude of the challenge we face. Because when you talk about reaching the speed of light, you are not talking about a difficult engineering problem. You are talking about quantities of energy so monumental that they make the energy production of entire civilizations seem insignificant. You are talking about numbers that defy human comprehension. Let's start with something modest. Imagine you want to accelerate a small object, say a baseball, that weighs 150 grams, to the speed of light. Excelente. He procesado el texto restante y lo he traducido según todas las directrices, manteniendo el formato, la precisión científica, la sustitución de números por palabras y el uso de terminología experta. It seems reasonable, doesn't it? It is just a ball. How much energy could it really need? The answer is terrifying. Using the relativistic energy equation, calculating the energy required to accelerate 150 grams up to 99.9% of the speed of light gives us approximately 3 billion joules. That is equivalent to the energy released by 717 kilograms of TNT, almost 3/4 of a ton of explosives for one baseball, and you would still be 0.1% away from the limit. Accelerating that same ball up to 99.99% of the speed of light would require approximately 9 billion joules, or 2.3 tons of TNT, up to 99.9999%, 30 billion joules, equivalent to 7 tons of TNT. The numbers grow exponentially, and to reach exactly 100%, you would need infinite energy, literally infinite, for one baseball. Now let us scale that to something more relevant for space travel. A small spacecraft, perhaps the size of an automobile, weighing 1,000 kilograms. Accelerating 1,000 kilograms up to 99% of the speed of light requires approximately 6.3 times 10 to the power of 18 joules of energy. To put that into perspective, it is equivalent to 1.5 million megatons of TNT, all of humanity's global energy production for approximately 4 years, concentrated into accelerating a single 1-ton ship, and you would still be 1% away from the speed of light. Accelerating that last 1%, from 99 to 100%, would require additional energy that eclipses everything before it. It is a progression that never ends, asymptotically approaching infinity. Let us consider specific energy sources. The most powerful nuclear bomb ever detonated, the Soviet Tsar bomber, released approximately 50 megatons of energy. You would need 30,000 of those bombs just to accelerate 1,000 kilograms up to 99% of the speed of light, 30,000 of the most powerful explosions ever created by humanity, and you would still not have reached the limit. What about solar energy? The sun produces approximately 3.8 times 10 to the power of 26 watts of total power. It is an incomprehensible amount, enough to power quadrillions of civilizations like ours. If you could capture all of the sun's production for one full second, all that massive energy, and direct it toward accelerating your 1,000-kilogram ship, you could reach approximately 99.99999% of the speed of light. Incredibly close, but still not exactly the speed of light. And you would have consumed one full second of all the sun's energy for a more realistic ship. Let us say one that could transport humans with life support systems, storage, fuel, and radiation protection. You are talking about at least 100 tons, probably much more. Accelerating 100,000 kilograms up to 99% of the speed of light requires approximately 6.3 times 10 to the power of 20 joules. That is equivalent to all the energy the sun produces in almost 2 seconds. All that radiant light that illuminates the entire solar system captured and concentrated to accelerate a single ship. And these calculations assume perfect efficiency. In reality, no propulsion system is 100% efficient. The best conventional rocket engines have efficiencies of perhaps 60 or 70%. Ion engines, among the most efficient we have built, reach maybe 90%. But even with perfect, hypothetical efficiency, the energy figures are prohibitive. Let us consider specific propulsion methods. Chemical rockets, the kind we use for all our current space missions, work by burning fuel and expelling hot gases. The best chemical rocket fuel, liquid hydrogen and oxygen, releases approximately 13,000 joules per gram when burned. To generate the 6.3 times 10 to the power of 20 joules needed to accelerate 100 tons up to 99% of the speed of light, you would need to burn approximately 48 billion tons of fuel. That is more than the mass of the water in all the Great Lakes of North America combined. And that is just the fuel, not counting the necessary oxidizer or the tank weight. Obviously, chemical rockets will not work. What about nuclear fission? Fission releases approximately 82 billion joules per kilogram of uranium. Much better. To generate our target energy, you would need approximately 7,600,000 kilograms of uranium, or 7,600 tons. More manageable than the Great Lakes, certainly, but still a massive amount of radioactive material to carry aboard a spacecraft. And this figure assumes that every uranium atom completely fissions, which never happens in practice. Nuclear fusion, the fusion of hydrogen into helium, the process that powers the sun, releases approximately 64 million joules per kilogram. For our target energy, you would need approximately 985,000 kilograms of hydrogen, almost 1,000 tons better, but still monumental. And remember, this is only to reach 99% of the speed of light, not 100%. The most efficient energy source we know is matter-antimatter annihilation. When matter and antimatter meet, they annihilate completely, converting all their mass into energy according to $E equals mc circumflex $2. It is a perfect, 100% efficient conversion. The annihilation of 1 kilogram of matter with 1 kilogram of antimatter releases approximately 9 times 10 to the power of 16 joules. Even with this ultra-efficient process, accelerating our 100-ton ship up to 99% of the speed of light would require approximately 3,500 kilograms of matter and 3,500 kilograms of antimatter, 7 total tons. It sounds almost reasonable, right? Except that producing and storing antimatter is extraordinarily difficult. all the antimatter ever produced by humanity would sum up to less than 20 nanograms, not even enough to see with the naked eye. Producing kilograms would require technological advances beyond anything on our current horizon. And again, this is only for 99% of the speed of light. Accelerating that final 1% would require exponentially larger additional amounts. 99.9% requires approximately 3 times more total energy. 99.99%, approximately 10 times more. 99.999%, 31 times more. The progression continues indefinitely, approaching infinite energy as you approach the limit. Some theorists have proposed collecting energy from astronomical sources. Stars produce massive amounts of energy. If you could build a Dyson sphere, a hypothetical megastructure that completely surrounds a star and captures all its energy output, you would have access to truly monumental energy. A Dyson sphere around the Sun could, in theory, provide enough energy to accelerate ships to significant relativistic speeds, but even then, you would be limited. A star like the Sun has a finite lifespan of approximately 10 billion years. It produces a finite amount of energy during that time. If you devoted the Sun's entire lifespan production to accelerating spacecraft, you could accelerate a finite number of ships up to near light speeds, but never up to exactly the speed of light. That final limit requires infinite energy, and the universe does not contain infinite energy. The total energy contained in all the matter of the observable universe, if completely converted into energy via matter-antimatter annihilation, is approximately 4 times 10 to the power of 69 joules. An incomprehensibly large number, but it is finite. And infinite energy is, by definition, greater than any finite number. No matter how much energy you gather, it will never be enough to accelerate something with mass up to exactly the speed of light. This is the fundamental energy barrier. It is not that we do not have enough energy now. It is that we will never have enough energy, not us, nor any future civilization. No matter how advanced, there is not enough energy in the entire universe to accelerate a single atom up to exactly the speed of light. It is mathematically impossible. The energy figures are not just daunting, they are absolutely prohibitive, and they tell us something fundamental. The cosmic speed limit is not a challenge to be overcome. It is a fundamental law of the universe, as immutable as gravity or the conservation of energy. And no amount of technological ingenuity can change the underlying mathematics. Among all the particles that exist in the universe, there is a special category that defies the rules we have been discussing. They are particles that have no rest mass, none, absolute zero. And because of this unique property, they not only can travel at the speed of light, but they must do so. They have no other choice. They can never move slower. They can never stop. They can never accelerate faster. From the moment of their creation until their eventual absorption, they move exactly at 300,000 kilometers per second, always. The most familiar of these particles is the photon, the quantum of light. Every ray of light you see, every radio signal that transmits information, every X-ray that penetrates tissues, is composed of photons traveling at light speed. Photons are literally packets of pure energy moving through space-time at the maximum velocity allowed by the universe. And because they lack rest mass, none of the restrictions we discussed earlier apply to them. When we said that accelerating something with mass up to the speed of light requires infinite energy, that statement is completely true. But photons have no rest mass. There is nothing to accelerate. They are created already, moving at light speed. An electron in an atom drops to a lower energy level, and the excess energy is instantly emitted as a photon that is already traveling at 300,000 kilometers per second. There is no period of acceleration, no gradual increase in speed. They simply exist in motion. And here is something fascinating. Photons do not experience time. Recall our discussion about time dilation. As you approach the speed of light, time slows down. At the exact limit, time stops completely. For a photon, traveling exactly at that limit speed, time literally does not flow. From the photon's perspective, if it could have a perspective, its emission and absorption are simultaneous events. A photon, emitted by a galaxy 13 billion light-years away, does not experience that 13 billion-year journey. For the photon, it is instantaneous. This creates an interesting conceptual paradox. We talk about light traveling through space, crossing vast distances over periods of time, and from our perspective, that is exactly what happens. But from the photon's perspective itself, there is no journey, no distance traveled, no time elapsed. It exists in a timeless state, connecting its point of emission with its point of absorption in a single, eternal instant. Photons are not the only massless particles. Gluons, the particles that mediate the strong nuclear force that holds atomic nuclei together, also lack rest mass and travel at the speed of light. However, gluons are never observed traveling freely. They are confined within atomic nuclei due to a property called color confinement. But within those microscopic limits, they move at light speed. For decades, physicists thought that neutrinos might also be massless particles. Neutrinos are extraordinarily elusive particles that barely interact with normal matter. Trillions of neutrinos from the Sun pass through your body every second without you noticing. They are so non-interactive that a typical neutrino could pass through light-years of solid lead without being stopped. If neutrinos had no mass, they would also travel exactly at the speed of light. But discoveries made in the late 20th and early 21st centuries showed that neutrinos do have mass, albeit extraordinarily small. Measurements suggest that the neutrino mass is at least 1 million times smaller than that of the electron, which is already incredibly light. Due to this tiny, but not zero, mass, neutrinos travel very slightly slower than the speed of light. Not by much, typically at 99.99% or more of the light speed, but not exactly at it. This discovery was significant because it confirmed that only truly massless particles can reach the speed of light. Even the smallest fraction of mass creates a barrier. Neutrinos, with their almost imperceptible mass, are subject to the same rules as everything else with mass. They can get very close, but they cannot reach the exact limit. So, why must massless particles travel at the speed of light? Why can they not move slower or faster? The answer lies in the fundamental equations of special relativity. The energy of a particle is related to its momentum and its rest mass by a specific equation. For particles with mass, there is a balance between kinetic energy and rest mass energy. They can have different velocities depending on how much kinetic energy they possess. But for particles with zero mass, the equation simplifies dramatically. Energy is directly proportional to momentum, with no rest mass term. And the only way to satisfy this relationship is by moving exactly at the speed of light. It is not a choice, it is not a preference. It is an inevitable mathematical consequence of having zero mass. Massless particles exist in a state where light speed is the only option. This is a fundamental difference between massive and massless particles. Massive particles have a rest frame of reference, a coordinate system in which they are stationary. You can, in principle, move alongside an electron in such a way that it appears to be at rest relative to you. But you cannot do that with a photon. There is no frame of reference where a photon is at rest. It is always moving at 300,000 kilometers per second, no matter how fast you move yourself. This creates a fundamental asymmetry in the universe. There are two classes of particles with radically different behaviors. Massive particles can exist at rest and can move at any speed less than light. Massless particles cannot exist at rest and must always move exactly at the speed of light. There is no middle ground. There are no particles that can choose to move sometimes at light speed and other times slower. And this distinction has profound consequences for the structure of the universe. Light, composed of massless photons, is the fastest possible messenger. Information cannot travel faster than light, because nothing can travel faster than light. This sets a fundamental limit on how quickly signals can propagate, how quickly causality can spread, how quickly we can communicate across the cosmos. Massless particles also show us that the cosmic speed limit is not arbitrary. It is not simply a number that the universe decided to impose. It is a direct consequence of the structure of spacetime and how energy, momentum, and mass are related. Massless particles reach that limit not because they are especially fast, but because it is the only velocity at which they can exist, given their fundamental nature. Curiously, Einstein's theory of general relativity predicts the existence of another massless particle, the graviton, the hypothetical quantum of gravity. If gravity is a quantized force, like electromagnetism, it must be mediated by particles, and those particles, according to the theory, should have no mass. Therefore, gravitational waves, perturbations in the fabric of spacetime, caused by accelerating massive objects, should propagate exactly at the speed of light, and that is exactly what we observe. In 2017, gravitational wave detectors captured signals from the collision of two neutron stars. Almost simultaneously, telescopes around the world detected light from the same collision. The signals arrived only seconds apart after traveling 130 million light-years. This confirmed that gravitational waves travel at the same speed as light, within extremely small margins of error. Gravity, like light, respects the cosmic speed limit. So, massless particles are not exceptions to the rule. They are confirmations of it. They demonstrate that the speed of light is truly fundamental, not just a limit for massive objects, but the natural velocity of spacetime itself. It is the speed at which causality travels, at which interactions propagate, at which the universe processes information. And this reinforces why we will never reach that speed. We are not photons. We have mass. And with mass comes inertia, comes the need for energy to accelerate, comes the relativistic increase in mass and the slowing of time. We are fundamentally in a different category of existence, subject to different rules. Massless particles show us what is possible at the limit, but they also remind us that that limit is closed to anything with mass. Photons travel freely at the speed of light because they have no other option. We cannot reach that speed for exactly the same reason. We do not have that option. Physics places us in separate categories, and no amount of technology can change the fundamental category to which we belong. There is a cruel irony in the laws of the universe. While we, trapped by our mass, can never reach the speed of light, space itself has no such restrictions. The fabric of the universe can expand, and indeed is expanding, at any speed. And in the farthest confines of the observable cosmos, that expansion is sweeping entire galaxies away from us, faster than the speed of light. They are not traveling through space at that speed, which would violate relativity. It is the space itself between us and them that is stretching, growing, expanding, and the result is the same. Those galaxies are permanently beyond our reach. To understand this, we need to talk about the expansion of the universe. In 1929, the astronomer Edwin Hubble made a revolutionary discovery. He observed that distant galaxies were moving away from us, and the farther away they were, the faster they moved. It was not that the galaxies were flying through a static space, it was the space itself that was expanding, dragging the galaxies along with it like raisins in a loaf of bread growing in the oven. This expansion is described by the Hubble constant, a number that relates a galaxy's distance to the velocity at which it moves away from us. The current value is approximately 70 kilometers per second per megaparsec. That means that for every megaparsec of distance, approximately 3.26 million light-years, a galaxy moves away from us 70 kilometers per second faster. A galaxy at 10 megaparsecs moves away at 700 kilometers per second. One at 100 megaparsecs at 7,000 kilometers per second. Now scale that. A galaxy at 14,000 megaparsecs, approximately 45 billion light-years away, would be moving away from us at approximately 980,000 kilometers per second. That is more than 3 times the speed of light, and it does not violate relativity because the galaxy itself is not moving through space at that velocity. It is the space between us and it that is expanding so rapidly that the distance grows faster than light can traverse it. This is the cosmic event horizon, although it is technically called the particle horizon or the Hubble sphere. It is the distance beyond which galaxies move away from us faster than the speed of light due to the expansion of space. And here is the devastating detail. Any galaxy beyond this horizon is fundamentally unreachable. No matter how fast you travel, you can never reach them. Even if you could travel at 99.999% of the speed of light, the space between you and those galaxies would grow faster than you can cross it. It is like trying to swim against a current that flows faster than your maximum swimming speed. No matter how hard you swim, the current drags you backward. You never advance. In fact, you continually lose ground. Those distant galaxies are being swept away from us by a current of expanding space that no ship, no matter how advanced, will ever be able to overcome. And it gets worse. For decades, astronomers thought that the expansion of the universe was gradually decelerating, slowed by the gravitational pull of all the matter it contains. It seemed logical. Gravity attracts, so it should be slowing the expansion, perhaps eventually stopping it, or even reversing it in a big crunch. But in 1998, observations of distant supernovae revealed something completely unexpected. The expansion of the universe is not slowing down, it is accelerating. Something is pushing the universe to expand faster and faster. Physicists call it dark energy, a placeholder name for a phenomenon they do not fully understand. Dark energy appears to be a property of the empty space itself, exerting a kind of negative pressure that drives the accelerated expansion, and it constitutes approximately 68% of all the energy in the universe. It is the dominant component of the cosmos, and it is causing the universe to expand exponentially faster over time. This has dire implications for the future. As the expansion accelerates, more and more galaxies will cross the cosmic event horizon and disappear from our sight forever. We will no longer be able to see them because their light will never reach us. The space between us and them will expand so rapidly that even light, traveling at 300,000 kilometers per second, will not be able to close the gap. Those galaxies will effectively cease to exist from our perspective, erased from the observable universe. And over time, our observable universe will shrink. In hundreds of billions of years, only the galaxies in our gravitationally bound local group, perhaps a few dozen galaxies, held together by their mutual gravitational attraction, will remain visible. Everything else will have been swept beyond the horizon. Astronomers of the far future will look up at the night sky and see almost nothing, only their own galaxy and its immediate companions, surrounded by absolute darkness. They will never know that there once were billions of other galaxies, because all evidence of them will have disappeared beyond the reach of light. But even now, in the present, vast regions of the universe are already unreachable. The observable universe has a radius of approximately 46.5 billion light-years. That is the limit of what we can see, determined by the age of the universe and the speed of light. Light from more distant objects simply has not had time to reach us yet. But the real universe, the total universe, is much larger, possibly infinite, and the vast majority of it is beyond our cosmic event horizon, unreachable, not only now, but forever. Think about that. There are galaxies out there, perhaps infinite in number, that we will never be able to visit, never be able to contact, never even be able to observe, not because they are too far away in the conventional sense, but because the space between us and them is expanding faster than the speed of light. They are physically unreachable, separated from us, not by distance, but by the relentless growth of space-time itself. And here is the truly disturbing part. Over time, even galaxies we can currently see will cross that horizon. In approximately 150 billion years, assuming dark energy remains constant, virtually all galaxies outside our local group will have disappeared beyond the event horizon. Any civilization that emerges after that point will live in a seemingly empty universe, with no evidence of the vast cosmic structure we see today. This creates an existential paradox. We live in a special epoch, a window of cosmic time, where the universe has existed long enough for galaxies and stars to form, but not so long that accelerated expansion has swept them all beyond sight. If humanity had evolved 100 billion years later, our astronomers would have observed a completely different cosmos, one almost empty, and they would never have discovered the truth about cosmic expansion, because there would not be enough observable evidence. The speed of light, then, does not only limit our travels, it limits our knowledge. There are regions of the universe that we can never learn anything about, because information from them will never reach us. The light from those regions is traveling toward us, but space is expanding so quickly that that light is losing ground, moving further and further away instead of closer. It is like a runner on a treadmill that is moving faster than he is running, moving backward despite striving forward, and there is no solution. Some have speculated about warp drives that could warp spacetime, or wormholes that could create shortcuts. But even if these ideas worked, which is extremely doubtful, they could not overcome the expansion of space itself. A wormhole connecting two points in an acceleratingly expanding universe would eventually stretch and break. A warp drive, if it could exist, would still be limited by the speed at which it can warp spacetime, and that velocity cannot locally exceed the speed of light. The cosmic event horizon is absolute. It is a frontier that divides the universe into two regions, the reachable and the unreachable. And due to the accelerated expansion, that frontier is moving inward, slowly shrinking the realm of the possible. We are trapped not only by our inability to reach the speed of light, but by the fact that the universe itself is conspiring to keep most of its vastness eternally out of our reach. This is perhaps the cruelest aspect of the cosmic speed limit. It not only prevents us from traveling fast, it prevents us from reaching the majority of the universe, condemning us to forever remain in a small bubble of the cosmos, watching helplessly as distant galaxies gradually disappear beyond a horizon from which they will never return. We are prisoners not only of our own mass, but of the expanding geometry of spacetime itself. The universe is vast beyond comprehension, and most of it will remain eternally beyond our reach, separated from us, not by distance, but by the fundamental laws of physics. We are alone in our corner of the cosmos, unable to attain the velocity necessary to escape, watching impotently as the universe pulls away. When reality imposes absolute limits, the human imagination desperately seeks loopholes. And in the equations of theoretical physics, particularly in Einstein's theory of general relativity, there are mathematical solutions that seem to offer ways to circumvent the cosmic speed limit. Wormholes that connect distant points in space, warp, drives that warp the space-time around a ship, extra dimensions through which we could travel. These ideas populate science fiction and capture our imagination. But when you examine the details, when you really calculate the numbers, each of these supposed solutions faces probably insurmountable obstacles. Let us start with wormholes. The idea is elegant. If space-time can be curved, then perhaps it can be folded over on itself, creating a shortcut between two distant points. Imagine a flat sheet of paper. 2 points on opposite sides of the sheet are separated by the distance across the paper. But if you fold the paper, bringing those 2 points closer, you could punch a hole that connects them directly. You would travel only a small distance through the hole, instead of the long distance across the surface of the paper. Mathematically, wormholes can exist in the equations of general relativity. They were first discovered in solutions found by Karl Schwarzschild in 1916 and developed more extensively by Albert Einstein and Nathan Rosen in 1935, hence the technical term Einstein-Rosen bridges. The mathematics work. Space-time can, in principle, form these tunnel structures that connect distant regions. But there is a massive problem. All the wormholes that naturally emerge from the equations are unstable. They collapse almost instantaneously, closing before anything can pass through them. The throat of the wormhole, the narrowest region of the tunnel, tends to contract and seal itself at near light speeds. To keep a wormhole open long enough for something to pass through it, you would need something called exotic matter with negative energy. Exotic matter sounds like science fiction, and basically it is. Normal matter has positive energy. Its gravity attracts. But to stabilize a wormhole, you would need matter with negative energy, whose gravity repels. This matter would create negative pressure, pushing outward against the walls of the wormhole to prevent it from collapsing. The problem is that we have never observed exotic matter in macroscopic quantities. Quantum effects can produce negative energy densities on microscopic scales for infinitesimal periods, but scaling that to the massive amounts needed for a traversable wormhole is completely beyond our capacity. Calculations show that to keep a wormhole open large enough for a person to pass through, you would need the negative energy equivalent of the mass of Jupiter. For a wormhole large enough for a spacecraft, multiple stellar masses of exotic matter. And remember, this is matter we have never seen exist in nature, whose properties would violate multiple energy conditions that we believe are fundamental to physics. You are asking for astronomical quantities of something that probably does not exist. Even if you could somehow create or find this exotic matter, creating a wormhole would require manipulating the geometry of spacetime at extreme scales. You would need to concentrate energies comparable to those of black holes in very specific configurations. It would literally be engineering the fabric of the universe itself, altering the fundamental structure of reality. No conceivable technology even comes close to these capabilities. And there is another problem. Even if you could build a stable wormhole, using it to travel faster than light creates temporal paradoxes. Relativity links space and time. A shortcut through space is effectively a shortcut through time. You could travel through a wormhole, arrive at your destination before you departed, return through another wormhole, and potentially interfere with your own past. The resulting paradoxes, such as the famous grandfather problem, where you kill your grandfather before your father is born, suggest that the universe does not allow such configurations. So, Let us move on to warp drives. The concept, popularized by Star Trek, but based on real physics, proposed by physicist Miguel Alcubierre in 1994, is that a ship could remain stationary within a bubble of normal spacetime while the space in front of it contracts and the space behind it expands. The ship would surf on a wave of distorted spacetime, effectively moving faster than light without locally violating the speed limit. Mathematically, the Alcubierre metric works. You can write equations that describe this spacetime configuration. But again, the practical requirements are absurd. Initial calculations suggested that you would need negative energy equivalent to several solar masses to create the warp bubble. Later refinements reduced that, but you are still talking about massive amounts of exotic matter distributed in very specific configurations around your ship. Harold White, a NASA physicist, proposed modifications that would theoretically reduce the energy requirements to something closer to the mass of Jupiter better, but still completely unfeasible. And that assumes that exotic matter exists and can be manipulated freely, which is a huge assumption. There are also problems with how you would control or steer such a ship, how you would communicate with it once inside the bubble, and how the crew would survive the intense radiation that would accumulate at the front of the bubble. Some physicists have argued that warp drives might be fundamentally impossible based on considerations of quantum mechanics. Quantum fluctuations of the vacuum could create feedback that destabilizes the bubble, or the extreme gravitational field required could collapse into a black hole. Classical mathematics allows warp drives, but when you include quantum effects, the picture becomes much less promising. What about extra dimensions? String theory, a theoretical framework that attempts to unify all fundamental forces, predicts that the universe could have up to 10 or 11 spatial dimensions, with the extra dimensions compacted on microscopic scales. If you could access those extra dimensions, perhaps you could travel through them, taking shortcuts that bypass the long route through our three familiar dimensions. But even if extra dimensions exist, and that is a big if, because we have never directly detected them, accessing them would require extremely high energies. The extra dimensions, if they exist, are curled up on scales near the Planck length, approximately 10 to the power of negative 35 meters. That is 1 trillion times smaller than an atomic nucleus. Unrolling or accessing those dimensions would require energies comparable to the Planck scale, approximately 10 to the power of 19 billion electron volts. To put that into perspective, the Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies of approximately 13,000 electron volts. You would need an accelerator approximately 1 quadrillion times more powerful, and that would only be to access the extra dimensions on the scales of individual particles, not to send spacecraft through them. Scaling that to macroscopic objects would require truly inconceivable energies. Some have proposed other exotic schemes: tachyons, hypothetical particles that always travel faster than light. The mathematics that describe them involve imaginary masses, the square root of negative numbers, which has no clear physical interpretation, and we have never detected a tachyon. If they exist, they are so elusive that they might be completely unobservable, which makes them useless for practical purposes. Manipulation of black holes. Rotating black holes could, in theory, have complex internal structures that allow for closed time-like trajectories. But crossing the event horizon of a black hole is a one-way trip. The tidal forces would tear you apart, and using black holes as portals would require control over objects with masses millions or billions of times that of the Sun. It is galactic-level civilization technology, if it is possible at all. Each of these ideas, as mathematically fascinating as it may be, faces practical obstacles, ranging from the extremely difficult to the physically impossible. They are not solutions. They are speculations, mathematical exercises that explore the limits of what the equations allow without seriously considering whether physical reality can implement them. And here is the fundamental truth. All these supposed loopholes attempt to circumvent the speed of light limit without technically violating relativity. Wormholes do not move you faster than light locally. They just create shortcuts. Warp drives do not accelerate your ship beyond light within its local frame. They are tricks, attempts to find loopholes in the rules, but the loopholes require conditions, energies, and materials so extreme that they might as well be impossible. Special relativity states that nothing can move through space faster than light. General relativity allows for manipulations of spacetime that could, in principle, create shortcuts. But the gap between mathematically possible and physically realizable is vast. It is the difference between writing equations on paper and manipulating the fabric of the universe itself. These are not viable solutions. They are mathematical dreams, demonstrating not that we can beat the cosmic speed limit, but how desperately we want to believe that we can. The cold, relentless reality remains. We are trapped, limited by the fundamental laws of physics, with no practical escape in sight. So, here we are, trapped, confined to a small bubble of the universe, by laws we cannot change, limits we cannot overcome. The speed of light is not simply a technical challenge waiting to be solved by some sufficiently advanced future civilization. It is a fundamental barrier woven into the very fabric of reality, as immutable as the existence of time or the structure of space. We have explored the reasons. Mass that grows toward infinity, requiring infinite energy to accelerate. Time that slows down to a stop, creating temporal paradoxes at the limit. The astronomical amounts of energy that even approaching the limit demands more than we could gather in multiple stellar lifespans. And finally, the accelerated expansion of the universe itself, sweeping galaxies beyond our reach, faster than any ship could pursue them. Each factor alone is enough to make light speed travel impossible. Together, they form an absolute prison. And this has profound implications, not only for our dreams of space exploration, but for our understanding of our place in the cosmos. Look up on a clear night, away from city lights. You will see thousands of stars dotting the sky. Each of those stars is so far away that its light has traveled for years to reach your eyes. You are literally seeing the past, a window into what the universe was like when that light began its journey. Proxima Centauri, our nearest neighboring star, is little more than 4 light-years away. The light we see tonight departed more than 4 years ago. If something dramatic happened there today, a massive flare, a stellar eruption, we would not know about it for more than 4 years. And if we wanted to travel there, even at an improbable 99% of the speed of light, the journey would take more than 4 years from Earth's perspective, more than 1 year from the crew's perspective. That is for our closest stellar neighbor. The Milky Way, our home galaxy, is approximately 100,000 light-years in diameter. It contains between 200 and 400 billion stars. And due to the cosmic speed limit, we will never be able to explore more than an infinitesimal fraction of them. Even traveling at 99.9% of the speed of light, which is completely impossible with any conceivable technology, crossing the galaxy would take more than 100,000 years from the terrestrial perspective. Multiple human civilizations could rise and fall in that time, and the Milky Way is just one galaxy among approximately 200 billion in the observable universe. Andromeda, our large galactic neighbor, is 2.5 million light-years away. The light we see from Andromeda tonight departed when our most primitive ancestors were barely beginning to use stone tools. A journey there even at extreme relativistic speeds, would take millions of years. It is effectively unreachable, and recall the cosmic event horizon we discussed. Vast regions of the universe are already separated from us by the accelerated expansion of space. Galaxies so distant that even if we traveled at the speed of light itself, we would never reach them, because the space between us is growing faster than we can traverse it. They are unreachable, not just practically, but fundamentally. They exist in a region of the universe causally separated from ours, a realm where we can never send signals, never travel, never have any influence. This defines our cosmic prison. We are confined to a small bubble of space-time, perhaps our local group of galaxies and its immediate neighbors, if we ever develop technology for slow interstellar travel. But the vast majority of the universe, with its countless galaxies, trillions of stars, potentially uncountable planetary systems, and alien civilizations that might exist out there, all of that remains eternally beyond our reach. And yet, there is something profoundly human in our reaction to these limits. We do not give up. We do not stop dreaming. The history of humanity is a history of pushing boundaries, of achieving what seemed impossible. We flew when we were told that humans would never leave the ground. We split the atom when it was considered the indivisible unit of matter. We landed on the moon when it was barely a point of light in the night sky. Why should this limit be different? Because this limit is fundamentally different. The previous limits were technological, based on our ignorance or lack of capabilities. We did not understand aerodynamics, so we could not fly. Once we understood the principles, we built airplanes. We did not have tools to manipulate atoms, so we could not split them. We developed the tools and succeeded. We did not have rockets powerful enough to reach the moon. We built bigger rockets and arrived. But the speed of light limit is not based on ignorance or lack of capabilities. It is based on the fundamental laws of physics. It is not that we do not know how to reach the speed of light. We know exactly why we cannot. The mathematics are clear, the equations unequivocal. Reaching the speed of light requires infinite energy, and the universe does not contain infinite energy. It is not a matter of better technology. It is a matter of mathematical impossibility. This does not mean we should stop exploring space. In fact, we must explore it precisely because it is so vast and we are so limited. Every piece of knowledge we gain about the universe is precious because we know we will never see the majority of it. Every planet we study, every star we observe, every galaxy we catalogue, expands our understanding of a cosmos of which we will always be distant observers rather than travelers. And there is beauty in that limitation. The fact that the speed of light is finite means that when we look into deep space, we are looking back in time. We are witnesses to the history of the universe unfolding before our eyes. The light from distant galaxies shows us what the universe was like billions of years ago, a natural time machine that allows us to study cosmic evolution from our corner of space-time. The limit also preserves causality, the notion that causes precede effects. If you could travel faster than light, you could in principle send information into your own past, creating paradoxes that would crumble all logic. The universe prevents this by making superluminal travel impossible. It is a built-in protection against logical inconsistencies, a rule that maintains the coherence of reality. And perhaps there is wisdom in our limitation. Perhaps we are not destined to be a galactic species that jumps between stars at will. Perhaps our destiny is to understand the universe, not conquer it. To use our minds to unravel the secrets of the cosmos, even if our bodies can never reach its farthest confines. Theoretical physics, astronomy, cosmology, these are forms of exploration that transcend physical limits. We can travel in thought, where we cannot travel in body. This does not make the prison less real. We remain trapped, confined to a tiny fraction of the universe by laws we cannot change. But it changes how we think about that confinement. It is not a defeat, it is a challenge. It forces us to be ingenious, to find ways to learn about the universe from our fixed position, to develop technologies that extend our senses, if not our bodies. Telescopes that can detect light from galaxies billions of light years away. Gravitational wave detectors that can capture the ripples in spacetime from black hole collisions on the other side of the observable universe. Robotic probes that can explore our solar system and beyond, sending data back across the vacuum. These are our tools for touching the untouchable, for reaching beyond our prison, even if we cannot escape it. And who knows what discoveries await. Physics has been repeatedly revolutionized by unexpected discoveries. Quantum mechanics, relativity, dark energy, each rewrote our understanding of reality. Perhaps there are aspects of physics we do not yet understand, genuine gaps in our knowledge that might, just might, offer possibilities we currently do not see. But based on what we know now, based on a century of rigorous experimental testing of relativity, based on the clear and unequivocal mathematics of Einstein's equations, the conclusion is inescapable. We will never reach the speed of light. We are prisoners of our cosmic corner, separated from the vast majority of the universe by a fundamental barrier that no technology can cross. And perhaps that is fine. Perhaps there is enough wonder, enough mystery, enough beauty in the portion of the cosmos we can reach to occupy us for millennia. Exploration is not always about reaching distant destinations. Sometimes it is about deeply understanding what is near, extracting every drop of knowledge from what is accessible. We are a young species in an old universe. We have existed for a blink in cosmic time. Perhaps our role is not to physically expand across the galaxies, but to expand our understanding, deepen our knowledge, and preserve and share what we learn about this extraordinary cosmos we find ourselves in. The speed of light limit tells us something profound about the universe. It has rules, structure, fundamental limits that define what is possible. We do not live in a fantasy realm where anything is possible with enough effort. We live in a physical universe with specific laws, and those laws have consequences. Learning to live within those limits, to flourish despite them, is perhaps the true measure of our maturity as a species. So, yes, we are prisoners of our cosmic corner, but we are conscious prisoners, capable of contemplating the vastness of our prison, of understanding the bars that keep us confined, of marveling at the fundamental laws that make our escape impossible. And in that understanding, in that awe, we find a different kind of freedom. Not the freedom to travel to distant stars, but the freedom to comprehend them. The universe has shown us its limits. Now, it is up to us to decide what we do within those limits. And if you decide to continue exploring these mysteries with us, if you want to keep unraveling the secrets of the cosmos from our small blue planet, then join Scientia Nocturna, Night Science. Every week, we explore the deepest questions of the universe, the mysteries that defy comprehension, the limits of what we can know. Subscribe, turn on notifications, and let us continue this journey together toward the confines of human knowledge. Because although we will never reach the speed of light, our curiosity knows no such limits. And in a universe that denies us physical travel, the intellectual journey remains infinite.